This is a Data Machines Incorporated Data 620, a fully transistorized mini computer from 1965. This particular one was used by NASA. It has these cool little stickers on it that say periodic check not required and have the NASA MSC logo on it. So this thing has some pretty exciting history going on with it. It was in use during the Apollo era. And this one does turn on. If I hit the power on switch here, you can see we get all these beautiful blinking lights on the front. I can hit reset here to halt it, and I can clear out some registers or set some bits, but things are not healthy. First and foremost, the core memory is not hooked up. This core memory may very well still have the last program that was run on it, which might be some NASA Apollo stuff. So we got to do everything in our power to try and pull that off safely. But even still, with the memory disconnected, with the front panel and the CPU, we should still be able to do something, and it's not doing like what we're expecting. The entire logic of the CPU is built up using cards like this. These are called VersaLOGIC. They contain a collection of germanium transistors, germanium diodes, and actually Zener diodes. This is a very early use of Zener diodes. They create a collection of NAND gates or flip-flops, and that creates the core logic of the machine that is all tied together via the absolutely insane wiring on the back plane. It's not really a back plane, it's just like point-to-point wiring. But I'm slightly worried about these cards because that's a huge amount of germanium transistors and germanium diodes. And when we did the Bendix G15, that machine has about 3,400 germanium diodes in it, and we found about a 2% failure rate on those diodes. Now, granted, this is about 10 years newer, and I'm expecting diode manufacturing quality to have greatly improved in that time, but I'm still expecting quite a few failed diodes on this. So we got to come up with some way to test these cards. And that presents us with a bit of a problem of scale. You see, there are 24 different types of modules in that machine, and each module has 40 pins for the card edge connector. Now, of those 43 are universal across all cards. That's power, which is going to be plus 6 volts, ground, and negative 12 volts. But the remaining 37 are wildly different from module to module. That means any given pin will need to be able to do input, read, output, and potentially provide some kind of high impedance state that represents what the bus would look like. That's a lot of functionality on a per pin basis. And to make matters worse, logic low is 0 volts, logic high is negative 12 volts. So if we want to build some kind of universal tester that will be able to test every single card using a microcontroller, we're going to end up with something like 10 to 15 parts required per pin in order to get that microcontroller to interface with this properly. That's like 300 to 400 parts required, and we're just going to end up troubleshooting the tester. And actually, it could be even worse than that, in that the tester is giving us weird results, and we end up trying to replace parts that are not bad. So I really think that the correct solution here is to scale this way back and keep it as simple as possible. And the simplest method that I can think of is just using some toggle switches and some LEDs. And I've got switches, I've got lights, I have some resistors for those switches and lights, and I even have a card edge connector here. So how am I gonna take all of this and build something meaningful out of it? And the truth is that I'm not smart enough to build something that gets all of the functionality that we need with this minimal amount of parts, but Robot256 over on the Discord is absolute legend. Came up with a design that I think is gonna work perfectly. I've got a printout of it here, but because the only functioning printer in my house is an old dot matrix, this is like a weird ASCII redrawing of it, but that's how simple it is. But it's, like, as you can see, it's incredibly simple. There are just 3 resistors, a 3-position toggle switch, and an LED. That's it. But this achieves an insane amount of functionality. When the 3-position toggle switch is in the up position, we have a connection from ground through the 470 ohm resistor straight to the I/O pin. This is emulating a PNP output transistor turned on. And that 470 ohm resistor limits the fault current to about 25 milliamps, which means that there's no hard shorts to ground. When the switch is in the middle position, meaning that it's open, this emulates an input pulled to negative 12 volts via the 5.1 k ohm resistor and the LED. And the 5.1K limits current to about 2 milliamps, so we're not going to damage anything that way. And finally, when the switch is in the down position, the 5.1K and 1K ohm resistors are in parallel, and this is going to emulate like a heavy load on a bus, which will show us if a transistor on the module that we're testing is weak. Like Robot 256, you absolutely crushed it with this design. It is a minimal amount of parts, it is incredibly simple to construct, but it achieves a ridiculous amount of functionality and safety. Like, we're not gonna damage anything by plugging a card into this. Like, you killed it, man. Thank you so much. However, there is one more big problem that we gotta overcome, and that is that if we don't know the exact schematic of the module that we have plugged in and that we're testing, we won't be able to make any sense of what the LEDs are telling us or know what position the switches are gonna need to be in. And none of those schematics exist. The original documentation didn't survive. Wait, let me correct myself there. Those schematics didn't exist. I went through and took pictures of the front and back of every single different type of module. I threw them up in a GitHub, threw the link onto the Discord, and I am still blown away by this. They all got reverse engineered. I myself reverse engineered only about 4 or 5 of the modules, but everybody on the Discord jumped in, and I'm gonna read some names here because every one of these people are legends, and I want you guys to go in the comments and thank all of these people, because without their help, we would not be able to do what we're gonna do today. So X, Bruce273, Tom C, Roy 2100, Robot 256, Kale Ren, I don't really know how to say that one, Sanosuke, Grabhanem, I again don't know how to say that one, and Nevitz. All of these people jumped in and started reverse engineering the modules based on the pictures alone, and some of them are incredibly difficult, but now we have schematics for every single module. And let's go through and talk about those, but first, I want to build this tester first. So let's build the tester, then we'll talk about what the different modules are, plug some of them in, and see how they work. Let's start with figuring out just how much space we need for our toggle switches. Looks like they're about 7.9 millimeters wide, so let's give them an even 10 millimeters of space to make measurements simple. I found this piece of scrap steel out in the scraps bin, and it looks like it's going to be the perfect width. Time to break out the Sharpie and start placing down measurement marks. I'll start with the far edge of where the switches can be. Then at 10 millimeter intervals, I'll make marks for where I'm going to need to drill. And now that I've got my grid all figured out, I need to center punch at the cross sections, as this is where I'm going to punch holes for these switches and LEDs. The center punch made these perfect little divots that help keep the bit perfectly aligned. Then it's over to the drill press. This steel plate is decently thick, so lots of cutting oil and trying really hard to not get impatient is the key. I start with a small bit and slowly work my way up with bigger and bigger bits until I'm at the right diameters. And after I've got all the holes punched, I go through with a special V-bit that chamfers the holes so they're nice and smooth. Since this piece came from our scrap bin, it's all beat up and scratched, so out came the sander and I went to work cleaning up the metal. Now that the surface is much smoother and cleaner, I can inspect all the holes, and some of them needed some extra cleanup with the file. Now before we move on to finishing work, let's mock everything up properly first. There we go, switch panel, edge connector, and power supplies. Using the switch panel as a bit of a template, I'll mark out all the alignment and mounting holes, then I'll temporarily mount everything to the backing board, starting with the edge connector. To get the switch panel mounted, I need some standoffs, and I happen to have this copper pipe hanging out in, you guessed it, the scrap bin as well. So I'll slice off 4 little standoffs, then set the switch panel on top of them and screw it down tight. And finally, how to mount the power supplies. Ultimately, I decided a spring over the top of them could get the job done. All right, I'm liking that. Let's make it look good now. First is sanding the wooden base with 60 grit to smooth it out and knock down any unevenness. After making sure the surface is now clean after sanding, I will stain this with some dark walnut stain using a shop rag to apply it. While that dries, I'll jump out and put a couple of coats of brown paint on the switch panel as well. After letting both of those dry for a full day, let's start getting this thing together. Turns out 10 millimeters isn't quite enough space for the toggle switches. The washers ended up slightly overlapping each other, making it a right pain to tighten down. Still, I soldiered on and got all the toggle switches secured down nice and tight. Then I moved on to the LEDs. I first just dropped them into place and made sure they were aligned correctly. Then I went through and temporarily held them in place with hot glue. Once they were secured, I could start laying down the 1K ohm resistors. With all of them laid out and lined up exactly how I wanted, I went through and soldered them to one leg of the LEDs. I then tied the other leg of all of the LEDs together like a giant bus. This is where our negative 12 volts goes. Rinse and repeat this process for the 5.1K and 470 ohm resistors, and with that all soldered in place, it's time to get the card edge connector wired up. It was absolutely a pain to get this done right. So much so, footage got a little scarce through here as I fought frustration. But ultimately, all 40 connections from the edge connector got pigtails plugged in, and then the other end of those pigtails got soldered on to a pair of DB25 ports. And if you thought everything up to this point sounded mind-numbingly tedious, let me tell you, that was just a preview of what was to come. The middle pin of all 37 toggle switches needs to be connected to the appropriate corresponding pin on the DB25 pair. Turns out nearly 40 wires trying to pass through the same place is a little much. Eventually I got it all soldered up and went through to double check with the multimeter. I had 2 pins shorted together and also managed to get off by one about halfway through. After a little rework, it came out looking absolutely brilliant though. Everything is neatly routed, so if I need to troubleshoot the tester in the future, it should be relatively straightforward. We're still missing power though. Let's get those generic power supplies mounted. After screwing down the spring clips and then hooking the spring in place, the power supplies slide right in and are held surprisingly well. I set one for 12 volt and the other for 6 volt, and then went through and soldered their power wires to all the appropriate buses under the switch panel. And now it's time for final installation. I'll flip the switch panel over, get it perched on the standoffs, and then screw it down nice and tight. That came out looking absolutely stunning. I am beyond happy with how this thing looks. It's almost a shame to have the switch panel turned right side up because the underside of it I think looks amazing with all of the wires and resistors going in all the different directions. But once it is right side up, you are greeted with 37 toggle switches, 37 LEDs. I just think this thing looks absolutely epic. The only part of this entire thing that lets it down are the somewhat modern power supplies. But in the future, if we want to make this thing truly period correct, we could swap these out for something a little more appropriate to the 1960s. But this, I think, is going to work absolutely perfectly. Now, it's not going to be able to check every single different type of card in the machine. There are 202 cards in total, but the core memory and the I/O box seem to be missing a couple of cards, so that number may not be quite accurate. So far, I've come across 24 different types of cards, and this should be able to confirm most of those. But there's definitely some in the core memory that this is not going to be capable of checking because those use like transformers and they're expecting transients and things like that. And this thing is just purely DC. So when it comes time to check those cards in the future, we can actually just unplug these little DB25 connectors here and plug in a different type of tester. And we can then plug a core memory card into here and have a little microcontroller that's specific to that core memory type card and do testing that way. But for the CPU, I think this is going to cover pretty much every card that is in the CPU. So the CPU has 100 cards in total in it, and there are 11 different types of cards. 36 of them are GA112-2s or GA27-1s. 16 are Reg 04s. 16 are ARI01 or 02. 11 are FF34. 10 are LD312 or LR312. 8 are a PA24-2. Then we have 1 GR26, 1 CIO1, and 1 XC31. And I think this tester can test every single one of those cards with the exception of XC31, which is the clock card, which we know is good already because we've been able to put the scope on the clock pins on the CPU and see it twiddling away. Now the GA112-2 and the GA27-1 are the most common. They make up a full third of the cards in the CPU. And the 112 has 12 2-input open collector NAND gates on it, and the 27 has 6 4-input NAND gates. 4 of those 6 are also open collector. Now the next most ubiquitous is Reg 04. That has 5 buffered SR flip-flops. This should be able to set and reset each individual flip-flop, but we're gonna have to give that a test to make sure that it's capable of that. ARI01 and ARI02 are the 1-bit bit slice adders. There's logic and a lot of these are like super confusing. Even looking at the schematic, I haven't quite fully figured them out. FF34, of which there are 11, has 4 SR flip-flops with the global reset. We should be able to test that one as well. LR and LD312 have 12 inverters. One of them is open collector and the other one is not. PA24 we think is a power amplifier with 4 buffered 4-input NAND gates. And then finally the GR26-1 has a bunch of 2-input NAND gates with 2 outputs. This one's also a little strange, but we should be able to test it if we know the pinout of it. So knowing that we should be able to test all the cards, how do you test a card with this thing? Well, there's some things here that are going to catch us out if we're not careful. The biggest one is that this is all pretty much negative logic. So the Data 620 uses 0 volts to be a logic low and negative 12 volts to be a logic high. All of our LEDs are going to illuminate in the reverse. So if the LED is off, that is a logic high, and if the LED is on, that is a logic low. Now, currently we have a GA112-2 plugged into this, which has 12 2-input open collector NAND gates on it. So what that means is that the output is always going to be a logic high unless both inputs go to a logic high, at which point the output will go to a logic low. So if we look at the schematic, we can see that every single pin of the GA112-2 is in use except for pin 4. Pins 1, 2, and 3 are the power, and then I have all of my switches and LEDs laid out here with the least significant bit on the far right. So this bit is going to be pin 4. This one all the way over here on the far left is going to be pin 40. Now I have all of the switches in the middle position, which is going to emulate an input pulled to negative 12 volts via the 5.1K in the LED. Negative 12 volts is going to be our logic high. So with all of these in the middle position, it means that all of the inputs to the NAND gates here are going to be logic highs, which means the LEDs are going to be off. And the output should be logic low for every single NAND gate, which means that the LED is going to be on. Let's flip the power switch here and see if that is truly the case. Yeah, that looks so cool. Oh, that looks awesome. But we can see that we have 12 LEDs lit up with the 2 LEDs to the right of each one currently off. Looking back at the schematic, we can confirm that pin 40 is the output, and then pin 38 and 39 are the 2 inputs to the last NAND gate that is on this card. Now the output is open collector, but it's important to note that when we have the switch in the middle position, there's a pull down to negative 12 volts via a 5.1K. So our open collector outputs will actually work and test just fine with this design. Now if I want to test that specific NAND gate, that's going to be these 3 LEDs on the very end here. Now I'm not going to touch the switch for pin 40 because we want that to essentially just stay as that pull down. But these 2 switches here, if I toggle one of them down, we can see that that LED comes on, which is now a logic low. And a logic low and a logic high into a NAND gate means that the output is going to be a logic high, and we can see that the output LED flipped off, so that NAND gate did exactly what it was supposed to do. If we move over to the next one here, that's the output. These are the 2 input. We can check that one. It's working absolutely perfectly as well. Now, if I take the output here and I push the toggle switch up, this is going to emulate a heavy load on the bus, and it'll tell us if the transistor is weak. And we can see that the LED got a whole lot brighter. And if I do it here, the LED got a whole lot brighter. Now that brightness tells us that the transistors on this one are plenty strong. Even with a heavy bus load, they can still drive that with no problem. Now let's switch over to the GA27-1. I think I mistakenly earlier said that this has 6 4-input NAND gates on it, but it actually has 7 4-input NAND gates on it. And with all of the switches here in the center position, that's going to be nothing but logic high inputs to all 7 NAND gates. So the outputs we are expecting to go to logic low, which means that the LEDs should turn on. Let's flip the switch and find out. 1, 2, 3, 4, 5, 6, and 7. We can see all 7 of our NAND gates turning on perfectly right there. Now the layout here is a little different than the GA112, as to be expected. Pin 40 here is just a 2K ohm pull down to negative 12 volts, so we can completely ignore that because there's nothing really to test there. Pin 39 is going to be the output, and then we have our 4 inputs next to it. So if we flip any one of those inputs on, the output should go off. Yeah, so we can see that we have currently 4 logic low inputs going into our 4-input NAND gate. The output is logic high, which the LED is off. In order to turn that LED back on, all 4 of these inputs must go to logic high. The output goes to logic low. The LED turns on. And we can just soldier right on down the line here, testing the next 4-input NAND gate. And it is also working perfectly. Next, let's try a flip-flop. This is the FF34 card. There are 4 very complex looking flip-flops on this thing with a global reset. So when I flip the switch on here, we should see at least 4 groups of LEDs going on here. So let's flip the switch. And yeah, look at that. That's awesome. We've got 4 sets of 2, the output and inverted output from each flip-flop. And looking at the pinouts, that all lines up perfectly. Although it is interesting that the inverted output is still illuminating the LED. I was expecting a cleaner on and off. And I'm having a bit of a hard time wrapping my head around exactly how this flip-flop works, but we can tell right off the bat here that these 2 flops are in opposing states. So one is set and the other one is reset. So if I hit the global reset, that should unify their outputs. Let's give that a shot. And yeah, we can see that this one reset and now it's got the same output as all of the rest of the flip-flops on here. Now I've been messing with this a little bit off camera, and there are 4 toggle switches here, and I've tried every combination of these and I can't really get it to behave very well. I did discover that if I push this one and I flip these 2 at the same time, it takes a couple of shots, but I can get it to set, and then I can hit the global reset and it goes back to where it was. So we'll try that again here. There it goes. That time it took 4 tries. So clearly I don't understand how the clocking works on this very well, and this is the only flip-flop I can get that to happen on. The remaining 3 I can't get to do anything. So the clocking of the flip-flops may be tripping us up a bit here. It could be that it's expecting a pulse of a certain speed in order to get the transients working correctly to get it to flip and flop, and we just can't achieve that with the toggle switches that we have here. So we may have to design a different tester specifically for the flip-flops, but fortunately, we have these DB25 connectors that we can just unplug and plug a different tester into that goes straight into the card edge connector here and borrows the power supply. This is like a wonderful solution. I am extremely happy with how this turned out. Like honestly though, I'm like way more happy with how it looks. Like I accidentally created the most beautiful card tester in the world. This thing is just gorgeous. It's so cool. So I've got a ton of testing to do. I'm not gonna do that on camera because it's gonna be like super tedious of pulling all the cards out, plugging them in, flipping a bunch of switches. So probably I'll just fire Discord up and hop on and have a live chat with a bunch of people while we test a bunch of cards. So I wanna thank you guys so very much for hanging out with me while I built this, and I hope to see you in the next one.